Hello, so this is a revision video for AP Chemistry 3.1, Intermolecular and Interparticle Forces. This is a revision video, so only the essential information is covered. For more detailed explanations and for full video lessons, please check the links in the description below and visit chemistrystudent.com. Intermolecular forces, or IMFs, are forces that exist between molecules. And it is intermolecular forces that get broken or formed when molecular substances change state, for example in melting and boiling. There are several different types of intermolecular force that can form depending upon the properties and type of the molecules present. London dispersion forces, or LDFs, are attraction forces that exist between temporary dipoles in molecules that occur due to random movement of electrons. They are present in all molecular substances, even noble gases and nonpolar molecules. There are several factors that affect the strength of London dispersion forces: the number of electrons, the molecular size and shape, and the polarizability. The more electrons there are in a molecule, the greater the temporary dipoles that can form due to their random movement, meaning stronger attraction forces between oppositely charged temporary dipoles in neighboring molecules. The more surface contact there is between molecules, the stronger the interactions as well. Larger electron clouds around molecules are also more easily distorted, again giving stronger attraction forces. Dipole-dipole interactions occur between polar molecules with permanent dipoles, where molecules align so that positive ends attract negative ends of nearby dipoles. For molecules of comparable size, dipole-dipole interactions are stronger than London dispersion forces, and their strength depends upon the magnitude of the dipole moment, so how polar the molecules are, and the distance and orientation between the dipoles, so how close the oppositely charged ends of each dipole can get to each other. Dipole-induced dipole forces occur when a polar molecule induces a temporary dipole in a nonpolar molecule, with attraction between oppositely charged ends from different dipoles. The larger the dipole on the polar molecule, the greater the temporary dipole it can induce in a nonpolar molecule, giving stronger forces of attraction. Equally, the greater the polarizability of the nonpolar molecule, so the larger its electron cloud, the stronger the temporary dipole it can have induced on it, and therefore the stronger the attraction forces it can form as a result. Ion-dipole forces describe attraction between a charged ion and the oppositely charged end of a polar molecule. They are stronger than dipole-dipole forces and are fundamental in the dissolving process of ionic compounds in water. For example, positively charged ions being attracted to the partially negative oxygen in the H2O molecule, and negatively charged ions being attracted to the partially positive hydrogens in a water molecule. The strength of ion-dipole forces depend on the charge and sizes of the ions. The smaller the ions and the greater their charge, the stronger the forces of attraction. The magnitude and direction of the dipoles in the polar molecules also influence the strength of the forces. The greater the polarity of the molecule, the stronger the ion-dipole forces it can form. Hydrogen bonding is a special type of strong dipole-dipole interaction that occurs when hydrogen is bonded to nitrogen, oxygen, or fluorine, and the positively charged hydrogen in one of these bonds is attracted to a nitrogen, oxygen, or fluorine in another molecule, or a different part of the same molecule. Hydrogen bonds are highly directional, meaning they can only form with specific orientations, and are relatively strong, meaning for comparably sized molecules, hydrogen bonding is the strongest type of intermolecular force. Exam tip here: remember, when talking about the relative strength of intermolecular forces, it is essential you are talking about comparably sized molecules. London dispersion forces are weaker than hydrogen bonding and dipole-dipole forces for similar sized molecules, but for very large molecules, like the ones found in polymers and plastics, then actually London dispersion forces become really strong. In large biological molecules such as proteins, intermolecular forces are vital for maintaining structure and shape, for example the alpha helices and beta-pleated sheets in proteins. Interactions between molecules also often rely on intermolecular forces, such as for enzymes binding to substrates in chemical reactions.